Hi, everybody. I'd love to introduce Nikola Kovachki from NVIDIA, and I do a lot of work on connecting scientific research and machine learning, and we'll be presenting operator learning in this talk. Welcome, Nikola.
Thank you so much for having me. I really appreciate the opportunity to give this talk today. So this talk today, I'm basically going to talk to you about this concept of operator learning, why it's important to scientific computing, kind of what are some of the applications, and my main focus will be more or less the approximation theory of this, but I'll also give you some engineering applications. So I'll tell you what this problem is all about. We'll set it up, and then I'll give you various examples of architectures, as well as the approximation theory for them, at least what is currently known. And then I'll give a few engineering applications of how this can actually be applied in practice and why it's a useful thing to do. Okay. So just as a motivation for why we care about operator learning, generally, I'm interested in scientific computing. So I'm interested in solving a lot of the problems that I've shown here. So for example, we have something like fluid simulations, where we might have very complex domains like this car shown here. And we might care about, how does this car fare when it's going really fast within a fluid, usually air. So we might want to be able to simulate what the pressure on the car looks like so that we can compute certain quantities like the drag. And from that, we can try and, improve the design of the car to minimize this drag or any other kind of engineering problem that one might face. There's also, problems in material science where people care about really designing strong materials or the most kind of elastic materials. So we might care about, if you have some plate, given, say, I'll show an example later of magnesium that is hit by an incoming projectile of some kind. What is the stress along this plate? So we want to simulate it so that we can maybe refine the microstructure of this plate so that we can design a better, stronger material. Or we might care about something like predicting the global weather. So we might care about a situation where we don't necessarily know all of the physics. And the physics are interacting across multiple scales, but it's a place where we might have a lot of data. And in this setting, we want to use machine learning because, again, we don't know all of the physics. So it's going to have to come through some amount of data. And we're going to model it through our data-driven way. So generally, two large kind of motivating applications of this. There's one, speeding up computationally expensive simulations. So this is places where we kind of know the physics. This is fluids and materials, but the simulations are very costly, at least using traditional numerical methods. So we might want to use machine learning in order to speed them up. Or we're in a situation where we don't fully understand all the physics that's happening and that's interacting, but we do have a lot of data, and so we want to model this phenomena through the data. Okay, so the way I'm going to set up this problem is as follows. I'm going to think all the time in function space, and I'll kind of tell you why that's a useful way of thinking. So I'm going to assume that what we want to model is a map, which I'm calling here G-dagger. And this map will be one between two separable Banach spaces. So that's a very generic setup. And it means that X and Y here are really spaces of functions. So you can think about some mapping which takes in a function and outputs a function. Okay, and I'll give a very simple example of that in a little bit. And I'll consider all data as functional data. Again, no discretization. So not thinking of anything as a vector, but rather just as functions. So the A's and the U's here are truly infinite dimensional objects, which are functions. And I'll assume I have, say, n pairs of them. And the U's are simply the push forwards of the A's under G-dagger. Okay, and for kind of theoretical reasons, I'm either going to assume that A's come IID from some measure mu, which is supported on Banach space X, or I'll assume that the A's come from a priori known compact set K. Okay, and this is for the purposes of doing approximation theory.
Quick question, real quick.
Yep.
Why so generic? Normally, we expect from vector to vector, simple, concrete. You need some flexibility from functions. So, what are you going for?
What do you mean? You need some flexibility for functions?
Well, you like your setting is you map from a function to a function.
Yes, that's right.
Functions are very wiggly and complicated things. So, what phenomena are you trying to capture using functions?
A lot of phenomena. So all the phenomena I showed before are all functional phenomena. So I can think of, for example, the pressure or the velocity of a fluid in some box around this car. That's a function. Similarly, I can think of the stress all along this material. That's a function. Similarly, the state of the atmosphere, the temperature all around Earth, or the wind velocity all around Earth, or the humidity all around Earth, that's a function.
So when you're saying function, the intuition is meshes.
Well, you can mesh, so that's going to be important. So you can mesh, but I'm going to think and I'm going to design architectures before doing any kind of meshing. So of course, if you want to compute on a computer, right, we're going to have to mesh. Like there's no way we can actually practically work with functions. But the idea is to design and think for functions and then mesh later.
Got it. But yeah, that makes sense. So it could also be a time mesh. Like you can say the evolution over time could be a function, but it's from some coordinate space to the state of the world is kind of the intuition you're going for.
Well, maybe it would be helpful if I give this example now then.
Ooh, yeah.
So if we look at this elliptic PDE here, so this is a very simple problem. So we have an elliptic PDE with diffusion coefficients A and solution U. So this, you can use this to model, for example, the pressure in subsurface flow. So if I have something, if I have a fluid which is forced by a given function F, its steady state, and in a material with diffusion coefficients A, its steady state will be given by the solution to this equation, which will be U. And you can model the solution map of this equation for a fixed F as the mapping which takes A, which is a function. So an example of such a function is given here, and maps it to the solution U. Okay. So, and the discretization, notice that the discretizations of these can be arbitrarily varied, right? So I'm not thinking about, oh, this particular function given on this particular mesh, which I'm showing here, but rather I'm thinking generically, given on any mesh, this mapping a G dagger exists. Does that make sense?
Yeah.
Okay. So let me maybe just go back. The way I'm going to think about things is that so this is just the generic setup. So we're going to think of such mappings, and we're going to try to find mappings, again, which abstractly work on any kind of function, but are parametrized in some finite dimensional way. Okay, so we're going to try and find parameters or some kind of parameter space in our N, so that from our class of parametric maps, which we'll design, we can approximate this G dagger. Yeah, and we're going to measure error in one of two ways, depending on how our data comes. So either we're going to measure error in this Blochner norm, which is in an average sense over the measure mu, or we're going to measure the error in a uniform way over the compact set K. Okay. And again, so this is kind of the generic example. So this is a very easy example. I don't want to make this, this is not really an engineering application. This problem is relatively easy to solve with standard numerical methods. But I want to give this as an example because I want people to think in this way. I want you to just have this problem in mind as I go through this talk. And at the end, I'll give kind of more complicated things that one can do with this. Okay. So, like I said before, I'm thinking about discretization in a particular way. And so I just want to give a bit of a perspective on how I'm going to design these architectures. Okay. And the perspective that I'm going to use comes from numerical analysis. And it's a very simple thing. So if we just consider the heat equation very quickly and try to discretize the heat equations in two distinct ways. So if I discretize the heat equation with the Fourier-Euler method, then I get an iteration which looks this way. So I'm going to only semi-discretize it. In particular, I'm not discretizing it in space. I'm only discretizing it in time with time step h. Okay. So this iteration, which is on the left here, actually makes no sense as a function space iteration because the identity plus delta times the Laplacian is an unbounded operator. So in particular, if I start this iteration with some function uk, which has, say, cs regularity, then every single time I apply this, it loses 2 orders of regularity, right? So as an iteration, this is kind of a nonsensical iteration. On the other hand, if I discretize this with a backward Euler method, then what I have here is I minus h Laplacian inverse. This is a compact operator. And this iteration makes perfect sense in function space. So because I can apply this over and over and over, and I will never lose regularity of UK. You will stay in the same space. So because of this, what you get is essentially what's called the CFL condition in PDEs. So this means that when I discretize this Laplacian, I have to choose delta H, so sorry, just H, which is the time step of the method, to depend on how I discretize my functions UK. If I go on the left column. On the other hand, if I go in the right column, then it doesn't matter how I discretize UK in terms of choosing H. As long as I pick it so the method is stable, there is no CFL condition. Okay, so that's the kind of philosophy which I'll go by. Here, in this particular example, H, you can think of H as the cost of the method, right? If H is really small, then I need to take a lot of iterations of this method to get to my solution. And in particular, I have to pick the cost to depend on the discretization. If I go kind of in this unbounded setting. Here, the cost is decoupled from the discretization of UK. Okay, so that's the idea about how we're going to design these architectures. We're going to basically pick the so in a machine learning architecture, I'll call the cost of the method the parameters, right? And if I want to be in this column, then I can pick the parameters to depend on particular discretizations of the input and output function. If I go in this column, then I can pick the parameters in a way that is independent of these discretizations. And so then I expect to be to have a cost which is decoupled from the discretization of any particular functions, which are my inputs or outputs. Okay.
So, question: this smells a lot like the split between implicit versus explicit methods, with explicit on the left, implicit on the right. Is that right?
That's right. That's exactly right. That's so. But I want to stress that this is just an analogy, which I'm using to illustrate why I want to pick parameters in the way that I want to pick them. Okay. And I'll show you an example that this works. So I'll talk about the specifics of the architectures later. But if you just take a unit and you look at different resolutions, so I'm looking at this problem, and I'm taking data which is discretized on different grids, and then I'm actually retraining the architecture with the same exact data, just given on different resolutions of the same grid. And then I'm looking at a test error. So if I take a unit which is discretized to be parameter dependent, what I'll see is this growth in the error. So as I increase the resolution, the error grows. On the other hand, if I design some architecture which has no parametric dependence on the resolution of the data, then I get something flat. So independently of how I've discretized my data, I get the same exact error. Okay, and this is useful because it means you can decouple how you design the architecture from the particulars of the discretization. Okay, it also means that you can use information at different discretizations. So in a lot of problems, especially in complex fluid simulations, you might have data that comes from all different kinds of meshes. And so if you design your method in such a way that it's able to use all of that information, then you have a lot more data available, right? And a hope would also be that you can actually transfer something you've learned at one parametrization to another. So if you have a lot of kind of maybe low resolution data, which is cheaper to obtain, then you might hope that you can transfer what you've actually learned to some higher resolution data, which you might have very little of, but still make good use of your lower resolution data. Okay, so with that, let me just give you a few examples of some architectures and go through kind of what is known in terms of approximation theory. So I'm going to start very simple with a linear method. And because in this case, we can kind of analyze it almost entirely. So the idea here just comes from model order reduction, and it's a very standard idea that's been used for a very long time. The idea is, so we have this operator G dagger, and to approximate it, we're going to try and make this diagram that I'm showing here commute approximately. In particular, we're going to find some encoder-decoder pair which is going to take functions, and then map them onto some finite dimensional space, Rm. Then there will be some nonlinear map, which maps this now vector to another vector in Rn. And then we're going to have another decoder, which takes this n numbers and spits out another function in the space y. Okay, so this diagram here can never truly fully commute, because unless G dagger has actual finite dimensional structure in it. But what we're going to hope is that it can be well approximated by something finite dimensional. And then depending on what G dagger is, we can say how well it can be approximated by something finite dimensional. Okay, so again, ED are a linear encoder and decoder pair. So linear maps from X into Rm and from Rm and into Y. And the only nonlinearity here is going to be this phi. And we can choose different kinds of ways of parametrizing phi. A standard one will be a neural network, okay, just an MLP. And this is the approximation class, is basically just the composition of the encoder, phi, and the decoder, okay? And the first question you can ask about this is, in what level of generality does this diagram approximately commute? And it turns out that the answer is incredibly general. So here are two kind of what you can call universal approximation results, is that if you have X and Y separable Banach spaces with something called the approximation property, which is a very standard property to do any kind of approximation theory, it means that on any compact set, you can resolve the identity as a limit of finite rank operators. It's kind of a standard thing to be able to do any kind of approximation theory with. So that's a very general assumption on the two input and output spaces. And if we take G dagger to be continuous, then we can always find in the uniform norm for any compact set encoder, decoder, and a continuous map between them, for which we have this universal approximation. And similarly, if we talk about average approximation, then for any probability measure on X and any G dagger that is P integrable, we can again find an encoder-decoder pair and phi for which universal approximation holds. Okay, so the above diagram and this kind of class of operators that I've defined here is a very general one. It can approximate pretty much anything we might care about in practice, is what this means. But this says nothing. So this just says universal approximation. It says nothing about how large we actually have to pick M and N for this to happen. Okay, so that's in this next theorem. It turns out that things. Sorry. Before I go on to that, I'll just give you a simple instantiation of this, and this is widely used in model order reduction. So if we take X and Y to be Hilbert spaces, and again, so mu is again a probability measure on X, G dagger will be P-measurable, P-integrable, and phi will be a neural network here. Then the above idea can be instantiated through just PCA, basically. So you take the covariance of mu, you find its eigenfunctions, you take the covariance of the push forward of mu under G dagger, you find its eigenfunctions, and then you can define your encoder to simply be the projection of your input function onto the first M eigenfunctions of the covariance of mu. And the decoder is nothing but a map which takes in a vector and expands it out as a sum on the eigenfunctions of the covariance of the push forward of mu. Okay, so this is a very simple architecture, and then your phi can be a neural network. So essentially, the way this architecture works is you take your function, you project it onto some M coordinates, you feed that into a neural network, which gives you M numbers, and then those M numbers are expanded as the coefficients on basis functions, which are given as the eigenfunctions of the covariance of the push forward of G dagger underneath. Okay, and there's other things you can do. You can try to learn these bases, but I'm not gonna get into all of that. This is just a very simple architecture. E is linear, D is also linear, and the only nonlinearity we try to capture here is phi. Okay, and we can now actually analyze this and prove the following. So just notationally here, I'm gonna say that alpha, The sequence of alphas are going to know the eigenvalues of the covariance of mu. Sequence of betas are going to be the eigenvalues of the covariance of G dagger, pushing forward mu. Then, so previously, we had this universal approximation theorem, which said that on average, the difference between G dagger and G can be made epsilon small. Once I actually specialize to the architecture that I showed you before, then you can decompose this error in the following way. So there's this NN term here, which I'm hiding, and I'll talk about in a little bit. So this is the error from your neural network approximation. Then there's this term here, which is a Monte Carlo term. So this says that as I increase the number of data, capital N, this term can go to 0. So this is a Monte Carlo term from empirically approximating the covariance of mu and the covariance of G dagger, pushing forward mu. And then you have these tail end sums of the eigenvalues. So whatever is, since you're doing a finite dimensional approximation, right, you're cutting off at M in the input space, and you're cutting off at N in the output space, then the tail end of these covariances show up, okay? So it turns out that for generic operators, so if I'm trying to just approximate some very generic G, I can actually put a lower bound on this, and the lower bound is given by the tail end of the output covariance. Okay, but this can be really, really, really slow. So this can be, so if G dagger, for example, is smoothing, then one can show that this sum can be asymptotically like n to the minus s, where s is whatever the smoothing parameter is. And if you plug this in to what one gets from this neural network term here that I've hidden, then you will get that this rate is exponentially slow in n. Okay, so I need an exponentially large amount of finite dimensionalization, n, or an amount of basis functions that I'm projecting onto, to be able to approximate up to epsilon. And for just the generic G dagger, which is just continuous, that's the only assumption we make on this map, then things can be even worse. In fact, this tail end sum can go like 1 over log n, which means that this nn term here can be doubly exponential in n. Okay, so this, I would say, is the first manifestation of what I'll call the curse of dimensionality, which will show up quite a few times. And this curse of dimensionality occurs for this particular method because it's a linear method, because all I've done here is use this d to project onto n eigenfunctions. Okay, so d here is a linear map, and because d is a linear map, the space y is kind of too large to be approximated efficiently, and there will always exist operators G dagger for which you need an exponential number of parameters to approximate efficiently. Okay, so this is kind of a motivation to why we shouldn't try and design methods which are nonlinear. Okay, so that brings me to kind of the next point, which is nonlinear approximation. And this is a very simple idea. So you just think of neural networks, which will be nonlinear, but you think of them in a space of functions. Okay, so I'll make a few more assumptions here on my spaces x and y, so I can make this concrete. So x and y here will be function spaces, and in particular, there will be function spaces over a domain, a bounded domain omega in Rd. Okay. And now I'll look at a family of operators, which is given as a composition of kind of simple operators. Okay, and this essentially mimics. It doesn't mimic. It is a neural network structure, but it's just conceived in infinite dimensions. Okay, and the simple operators that I'm going to consider look as follows. So let me go through the structure a little bit more in detail. So the structure is you have a non-local term, which is the main term in this, and the non-local term is given by a kernel integral operator. So we take our input function a, and we integrate it against a kernel, kappa L. And then to that, we then multiply it by a local linear term, which is this W. We add the two together, and then these two go through a pointwise, so local nonlinearity. So there's two local terms, which are this linear W, as well as this nonlinear sigma. And then there is a non-local global term, which is given by this kappa O. So within this kind of framework, if you start thinking about discretization, then this really gives you more or less most of the architectures that really are used in deep learning today. So this additive term here is just used as kind of a residual network. So you don't technically need it for any kind of universal approximation or anything like that. But people have shown that just practically things work better if you do have it. The non-local term is a generalization of if in an NLP you have a weight, so now the weight is replaced by a kernel instead, and then integration is performed. And then the nonlinearity is the simple standard pointwise nonlinearity that you do in a neural network. And here, you're allowed to vary it. You're allowed to also parametrize it if you like, but also you're allowed to fix it. And so you can make this into a convolutional neural network, for example, if I choose this kernel to be translation invariant, and if I parametrize it on some small amount of grid in omega. Okay, but that is generally an issue with convolutional neural networks because the way that they parametrize this kappa L is grid dependent. Point here is that we're gonna think and we're gonna conceive of this architecture in a purely functional way without any parametrization, and only do that once we actually need to do something in practice. Okay, but this is more general, and kappa here can be, of course, matrix valued, and so on.
So, question.
Yes.
So it seemed like the last variant was I use PCA to project my original data done linearly.
Yes.
Then I use a neural net, which seems very much like this, and then I use PCA to undo it. Whereas here, I mean, I'm seeing the neural net. The weights and the sigma is literally neural net.
Yes.
Kappa seems that's where you would hide the PCA in this kappa, right?
No, there's no PCA here. So this is a completely different architecture. There's no PCA
because it seems like the shape is very similar.
Right. So here
that was the neural net. And here, neural net seems to be primary in the second slide, whereas in the previous one, neural net was a little addendum.
Right, but because here, this is just a standard neural net. So this can be whatever you want. This can be an MLP. This can be a convolutional net. This can be anything you like. Here, this is a neural net, but it's written in function space, right? So the whole architecture here is, you can think of as one neural net. Here, there's only one. Here, you just have a standard neural network, right? But this doesn't have to be a neural network. This can be any map from Rm to Rn. Here, when you've written things in this way, you've really found something which is a map between the function spaces X and Y, right? If I don't think about any kind of parametrization, each of these single simple layers is a functional mapping of A.
Okay, so maybe let me see if I can summarize this. In the previous one, you really had explicitly leaned into the encoder phi decoder.
Yep.
Here, you don't really have an encoder except this little kappa, maybe a little simple encoder. But for the most part, it's these structured nonlinear layers, and I think you're pointing to that forcing an initial linear transform and then linear like undo means that your convergence is slow, even if the middle phi is arbitrarily complicated. And you really want this structure to be consistently nonlinear to get better approximation.
That's exactly right. That's exactly right. That's exactly right. Yes.
Okay, thank you.
And yes, so right. So this is consistently nonlinear, and it will be okay. Maybe I should discuss what I mean by linear and nonlinear more generally. So we're always approximating nonlinear maps. So the G daggers will essentially always be nonlinear. But what I mean is between a method of approximation is linear or nonlinear, depending on what its range space looks like. So in this architecture, the range space of this method is the span of the first n eigenfunctions of this covariance. And that's a linear space within Y. And this is why I call this a linear method. On the other hand, in this method, the range space is a nonlinear manifold within Y. And this is why this is a nonlinear method of approximation. Does that make sense?
Yeah.
Okay. Okay, so again, for this kind of architecture, you can ask a similar question. Is this a universal approximator? And the answer is yes. So this will be a theme throughout. Almost everything is a universal approximation, but also almost everything incurs the curse of dimensionality. So we'll see that later. So here you can, getting away from all the details of this, this says that for a whole lot of spaces that one might care about in scientific computing, like Lebesgue spaces or soulless spaces or spaces of continuously differentiable functions, you can kind of pick any pairs of x and y that you like. And if you have some continuous operator between them, then the previous architecture, which I showed you, is a universal approximator. And so either in a uniform norm or in an average sense, you can approximate as finely as you want, so long as you pick kind of this kappa to be sufficiently complex and this W to be sufficiently large. And you can actually fix the activation functions. Yeah?
Yeah.
Okay. So let me just give you a few examples of instantiations of this architecture, because a lot of what's currently done in practice can be thought of as instantiations of this architecture. So like I mentioned before, convolutional neural networks can be an example. However, the way that they parametrize kappa L, I would say, is inconsistent with the function space point of view, because convolutional neural networks parametrize basically the function kappa on a few grid points, which means that the moment I change the architecture of my input function, I change also with it the discretization of kappa. So if you think about, zooming into a function, the kind of the support of the convolution kernel gets smaller and smaller and smaller the more I zoom in. And this is why this kind of parametrization is not really consistent, because you can't really use it to transfer what you've learned from one discretization to another, or you can't hope to even use it for different kinds of discretizations of the same function, because ultimately you'll learn different kind of features at different scales, and that just won't work. And I showed you an example at the beginning of it actually not working in practice. Okay, a kind of more consistent method of parametrizing kappa while still being convolutional is to do it through a transform method. So you can think of parametrizing kappa directly in, say, a spectral expansion. So I can expand kappa on, say, a few Fourier modes, or really any kind of basis functions that I like. And then all I have to do to compute this now convolution is compute the appropriate transform of A. So let's just think of T here as being a Fourier transform. So I parameterize kappa directly by its spectral coefficients. I then, when I have an input A, I take its Fourier transform, I pointwise multiply, and then I take the inverse transform. Okay, and that's the same as computing this integral. But now I've parameterized kappa in a way that is consistent to any discretization I might care about for A. Okay, and people have done this in a lot of different ways. People have used Fourier expansions, like I mentioned, spherical harmonic expansions. If your functions lie on the sphere, you can also use wavelet basis, or more generically, any kind of basis, any kind of eigenfunctions of the Laplace-Beltrami operator if you are working on some kind of complicated domain or a complicated manifold. So people in graphics, for example, use a lot expansions on the Laplace-Beltrami eigenfunctions. And the nice thing about this, well, now this is now actually a relatively fast method, because if I think about computing this integral and say I discretize my omega with n points, then naive computation of this integral, say through a Riemann sum, is n squared, but generally through a fast transform, one gets n log n. So it's a much more efficient way of computing this kind of integral. Okay, and of course there are also direct methods for computing this integral. So like I mentioned, you can just do a Riemann sum, Or you can try to be a bit more clever in how you do that. So you can try and do something like a multiple exponential. So this very much looks like what DeepMind's GraphCast is. It's essentially a multiple expansion of this kernel at different scales. You can also try to limit kind of the support of the kernel. And yeah, there's a lot of, practically there's a lot of things people have done in this space. So this is kind of how you put this in practice. What I want to discuss, however, is the approximation theory of this. And when does there still, so this is a nonlinear method, but it turns out that one still has the curse of dimensionality. And the question is, what does the curse of dimensionality look like in infinite dimensions? And what it looks like is exponential rate. So here, first one needs a notion of what a set means to be truly infinite dimensional. So if you remember before, I'm approximating over, here I'm just going to focus on approximating over compact sets K. Now, if K is intrinsically finite dimensional, then there will be no difference between the kind of the finite dimensional curse of dimensionality and the infinite dimensional curse of dimensionality. So I need to ensure that I have a notion of size which truly quantifies that K is infinite dimensional. And here the notion is what I'll call an alpha hypercube, which means that K contains functions within it which have a decay rate of j to the minus alpha, okay, for some alpha greater than 1. So any compact set K which contains such a hypercube, here the phi's are, just some orthogonal system on X. So as long as kind of the functions contained within K have a natural spectral expansion which decays slowly enough, and slowly enough here means at an algebraic rate, then K is large enough. K really is truly infinite dimensional. Okay, then one can show that even for a very smooth G dagger, so a G dagger which is S times Fréchet differentiable, there will exist one for which epsilon approximation by an architecture which I showed before has to have parameters which are lower bounded in a way that is exponential in epsilon. So again, I need an exponential number of parameters in epsilon to approximate just G dagger. So this is the kind of the I'm calling here the parametric curse of dimensionality, which is telling me that there will always be a bad map that I can't possibly approximate well. So I can approximate anything, but there will always be things that I cannot really approximate efficiently. Okay. However, so then we can ask the question, are there things that we can approximate efficiently? And the answer is yes. I'll give an example of that. But before I give an example of that, I want to set up how I want to study the things that we can approximate efficiently. So I'll call sigma m the class of operators G. So they can be from, so they can really come from any of the previous classes that I showed you before, for which the number of parameters that they have are at most m, and for which the size of the parameter is bounded by b. Okay, b here is really not important. The main part here, so I'm considering a space M of this parametric class, which has at most m parameters. Okay, and then I can ask something about this space. I can ask, what are the mappings that can be efficiently approximated by the things in sigma m? Okay, so this is the space A gamma. So A gamma is called the approximation space of sigma m, and is the set of all G dagger, which are continuous, and which I can approximate at a rate of m to the minus gamma. So why m to the minus gamma? Because this previous result told us what the curse of dimensionality looks like in infinite dimensions. It means that there are things that for which you need an exponential number of parameters to approximate. And here I'm asking, what are all the things that I can approximate at an algebraic rate? So for which I need an algebraic number of parameters to approximate efficiently. Turns out that this space is kind of a nice space. It's a this A gamma space. It's a quasi-norm Banach space, and so you can kind of study its properties.
Question about how you're using the word algebraically. Do you mean sub-exponentially or polynomially or something else?
Polynomially. So this is what I mean. So M here is the number. Remember that M is the number of parameters. So I want here. So what I'm saying here is that the best approximation of G dagger from sigma M decays like M to the minus gamma. This is in contrast to this, where the best approximation to G dagger from any G will be logarithmic.
Okay. So the quality of approximation improves exponentially fast.
Yes. No. So the quality of approximation improves exponentially slow.
Oh no, wait. So this is the number of parameters. So maybe I missed the way I thought you just swapped terms. Here's the number of parameter for a fixed approximation quality. Number of parameters grows exponentially fast, or is this the accuracy grows exponentially slow?
So the accuracy is epsilon, right?
I see. Okay.
And so for an epsilon, this has the for an epsilon accuracy and an exponential number of parameters in epsilon to get to epsilon.
In epsilon. Okay, good.
Yeah. Well, here, what I'm asking for is an algebraic number of parameters in epsilon.
Okay. Okay. Yep. Thank you.
So this is what I'll call beating the curse of dimensionality in this space. So here, I've shown you that there will always exist maps for which you need an exponential number of parameters in epsilon to approximate. And here, I'm asking, what are all the maps for which this doesn't happen, for which I get an algebraic number of parameters in epsilon to approximate? Does that make sense?
Yeah.
Yeah. So the thing about this space is in the infinite dimensional setting. This space is incredibly complicated, and even for very simple classes of G, we have not been able to characterize it. In finite dimensions, a lot of these spaces have been characterized. I'm not going to talk about that, but something I can tell you about this space, and really the only thing we kind of know about this space is that it's non-empty. So this is an example of something that does belong to the space. So if I consider, on top, if I consider here some kind of Navier, some kind of incompressible flow, so this can be either Navier-Stokes if mu is greater than 0, or it can be the Euler equation if mu is exactly 0. Then if I set this up problem correct, if I set up this problem correctly so that I always get uniformly bounded solutions in time, and I consider the mappings which give me some input flow and map it to the final time flow, so at a fixed t, then I can prove for a particular class that the number of parameters needed does indeed go down algebraically. Okay, so I'm not going to get into the details of all the regularity theory, but the idea is just that there are maps, and there are maps that people care about in fluid dynamics. Navier-Stokes and Euler are one of the most kind of solved equations in fluid dynamics. So these maps that we really do care about in practice can in fact be efficiently approximated with an architecture of this kind. Okay, so this is kind of good news, but unfortunately, this is almost all we can say about this space.
But actually, this is, to me, very good news, because Navier-Stokes is multi-scale, which seems like that would be one of the more difficult settings. Right. So do you have intuition for why you can't prove it, and kind of why multiscaleness does not break everything here?
Yeah. So the reason you can prove it is because we have we've come up with kind of efficient numerical methods which can approximate it. And what you can do is emulate such a method. So you can basically construct kind of a theoretical architecture which emulates a very efficient numerical method. And then you can prove that the emulation of this efficient numerical method can be done efficiently, essentially.
Okay, but is there then any gain if that's the construction?
So from the theoretical perspective, no.
Okay.
Right. So because exactly. So all I've set up here is something that emulates a numerical method.
Right.
And so you can ask, well, why not just use the original numerical method, right? And I'll tell you, well, yeah, you can. But in practice, and maybe I'll get to this a bit later, we do see tons of games. So you can think of maybe, we can try and construct some numerical method based on what we know, and we can prove that that's a good thing to do. But once you actually use this in a data-driven way, then it's finding something that is more efficient than the thing that we've been able to construct. But this at least shows that it is possible.
Right. Okay.
Unfortunately, doesn't say anything about practice. And so people have kind of done this for, here I'm showing you a result that we did for Navier-Stokes, but people have done this for kind of a whole host of other PDEs and other families of PDEs. And it turns out that precisely this approach that I just mentioned, where you take a numerical method which is efficient and you try to emulate it in an efficient way, works very well. And you can prove that tons of things that we care about in practice can be approximated efficiently. Another kind of line of work in this area has been holomorphic operators. So these are, kind of infinitely smooth analytic operators. Turns out that those can also be emulated in an efficient way. And you can kind of follow also the neural network way of thinking here and define a space, which naturally gives you efficient approximation. And this is the operator Barron space. Okay, I'm not going to discuss any of this in practice. The whole point of this is that we know essentially nothing about the space except that it's not empty, and we can, and people have kind of proven that there's a few operators here and there that belong to it. Okay, so now I'm going to move to kind of a different notion. So this is kind of this parametric curse of dimensionality was, this kind of second manifestation of the curse of dimensionality. The first one was the size of y, and the curse of dimensionality was from the fact that we were linear. Here we are in this setting, we're nonlinear, but we still have a curse of dimensionality. And now I'll talk about kind of a data curse of dimensionality. Okay. And to characterize the data curse of dimensionality, I'll generalize the notion of what's called an n-width. So here I'm going to, just for the case of simplicity, the space Y used to be a function space. Now I'm just going to take it to be R. So I'm going to think about mappings which take in a function and output a number. Okay. So X here will either be the space of such continuous functional. So again, X is still a function space. And we think about continuous mappings which take a function and output a number. Or we can think about an associated Bochner space of this. Okay. And then we can also think about such functionals which are S times, say, Frechet differentiable over a compact setting K. Okay. And here U denotes the unit ball of the space. Not super important. Okay. And now the way we define, so I do want to say that this encoder and decoder are not related to the original kind of PCA architecture that I showed. These are generic mappings. So an encoder here is anything which takes in. So now they're more general. They take in a continuous functional and they spit out n numbers. Or they take in n numbers and spit out a continuous functional. Okay. And we define the n-width of, say, the unit ball of all S times Frechet differentiable such functionals as the best encoder-decoder pair for the worst functional within M that we can reconstruct. Okay, so this says something about data, because data, you can essentially think about the encoder, because the encoder takes in the object that you're trying to approximate. So you can think about the encoder as gathering information about this object, and the decoder as anything which uses this information and tries to reconstruct. So this is really, you can think of this as any generic kind of algorithm, right? Because you gather data in some way, and here I'm assuming the way that I gather data is continuous, and then I use this data to reconstruct. Okay. And a particular, say, instantiation of this is if I assume that En is just a set of delta functionals. So En, the way that En is going to gather information here in this second box is by evaluating this G dagger on a few different A's, so on some set of fixed A's. And then based on this evaluation, I'm looking for anything that can take this and reconstruct it. Okay. And now I want to say something about this n-width. This is generally called a nonlinear n-width. And it turns out that you can say something about this n-width in very, very generally. So if I use my notion of the alpha hypercube as I did before, then what you can show is that this n width is lower bounded in a logarithmic way, okay, by n. So again, this means that, again, algebraic rates, which is the curse of dimensionality in finite dimensions, become exponential in infinite dimensions. Okay, so what this tells me essentially is that I will always need an exponential amount of data to reconstruct. So, or rather, there will always exist some operator, some functional, which is smooth. So it's S times for differentiable, but for which I'll still need an exponential amount of data in order to reconstruct it L, no matter what I do, with any kind of reconstruction algorithm or any kind of architecture that I try to come up with, I'll need an exponential amount of data, okay? There is kind of good news, and the good news, data curse, and that's here. So this says that if I look instead at the space of things that are efficiently approximate. So remember that A gamma was the set of maps which I can approximate at an algebraic rate, n to the minus gamma. Then the worst case in this set can actually be reconstructed at a data rate, which is now algebraic. So this essentially says that if I can be parametrically efficient, then I can be data efficient. So it kind of makes sense to study. It just connects the two concepts. So it makes sense to study parametric efficiency because it tells you something about data efficiency. Okay. So this is everything I wanted to show in terms of approximation theory. I have basically no time. So I will very quickly glance through a few applications of these ideas. Maybe the first one. Okay, maybe I just start here. So let's think about fluid dynamics a little bit. And let's say I want to kind of do the problem that I showed you at the beginning, where I have some wind turbine, and I'm thinking about fluid air coming in on one side of this turbine, let's say some fixed velocity. And then what I'm going to vary inside is the domain. So here, a car. So this is a mapping really from the domain of Navier-Stokes to the solution of Navier-Stokes, which can be the velocity. The thing I'm going to care about is the pressure on the surface of a car, because and the wall shear stress, because that can be then used to get drag information about the car. Okay, so this is a parametric model, and we ran some RAN simulations to create kind of a data set of only about 500 car pairs. Roughly the Reynolds number, the average Reynolds number is about 5 million in this simulation. And like I said, we're mapping the geometry of the car itself and maybe the inlet velocity to the pressure and the wall shear stress on the surface of a car, because from that we can compute drag coefficients. And so here's two graphs. So I'm not giving details about the architecture, but it's a kind of architecture that I showed you before. So one, if I look at, so two things, right? One is the fact that if I increase with such an architecture, if I increase the resolution of kind of how I'm representing this grid, then I get something that's consistent. I get an error that is always consistent, and in fact here decaying as I refine my error. And also, if I look at a full kind of cost accuracy trade-off analysis compared to the solver, which we used OpenFOAM to generate these simulations, then these machine learning methods are giving me 4 orders of magnitude of speed up compared to the solver itself. So here, basically, because it's an iterative solver, which solves this Rand's equation, you can go back and you can trace what drag coefficient gave you kind of at each iteration of this solver. And so you can compute the error before convergence and how many iterations you've needed to do for the solver to actually get to such an error. And then you can look at that and compare it against the machine learning method, varying, say, the number of parameters used to encode this network, and here the runtime. And we see kind of at a fixed error, which is here a relative error of like 3.5% in the drag coefficient, there is roughly a 4 order of magnitude speedup. So that's quite encouraging. So this tells you that this is really, you can really gain a lot if you're willing to tolerate this level of error. Then this really gives you a lot. And how do you get this error down? I mean, likely you need to like offline generate more data. You can try and make the model bigger and bigger, but as you can see here, you stagnate at some point, right? So here you really run into the data curse much more. I will skip this materials problem because I don't have time. And I'll just maybe talk about weather a little bit. So I can also try to do this for weather. There's tons and tons of data for weather. So here we looked at this data set called Error 5, which is from ECMWF. And this is roughly, I want to say 18 terabytes of available data, which is all measurements of things like the humidity, the pressure, the wind velocity, at different kind of places within the atmosphere. And then this data has been reassimilated with a physics model. And so you can try to kind of mimic this dynamical system with a machine learning model using all this data that you have. And this actually tends to work quite well. So one of these architectures that I showed you before, which now uses spherical harmonics as a parametrization, can essentially get very close to, or beat in some cases, the kind of state-of-the-art IFS model from ECMWF, which is something that is fully physics-driven and has been developed for many, many years. And having something like this, which is as accurate and can also run very fast, is really important, because then you can kind of try and start to construct things like probabilistic models, and you can try to predict extreme events. So here I'm showing you an ensemble simulation where we've ran 1,000 of these versus running 50 of these. So at a particular spot, so we've picked here a particular spot where we know a hurricane is going to happen, and we've ran only 50 ensemble members. And you can kind of see that this will tell you, well, it's unlikely that anything kind of extreme will happen. On the other hand, if you can actually afford to run 1,000 of these, which you can because it's a machine learning method that is kind of fast, then you actually get the tail end of this extreme winds, and you can see that this here that there actually is a positive probability of you finding this hurricane, which really did in fact happen. Okay, so I'm just going to stop here. I'm now fully out of time. Sorry, I couldn't get into the applications more.
No, this is already great. Like, let me actually try and making a connection. So, to what extent are you leveraging knowledge of the original mesh? Because I mean, this is like Gino is like geometry informed. So,
right. Yeah. Okay. So you're asking about this.
Yeah.
Yeah. So a lot of information about. So I guess you're asking how am I informing this? How am I informing this mesh? So this is done by an SDF. So you can, and that's what latent grid means. So basically, you can put all your meshes in a fixed box.
Mm-hmm.
You can discretize this box in kind of any way you like. And then for each point of discretization, you can compute the distance from that box to the mesh, right? And then you can use that as an input function. And here what I'm showing is that as I refine the discretization of this box, these methods get better and better. Or, I mean, they stagnate at some point once you kind of hit enough information.
Right. And is that what you use for weather? Or no, those are harmonics.
No, for weather, it's a completely different architecture.
Mm-hmm.
For weather, it's an architecture based on spherical harmonics. So here, this T is a fast spherical harmonic transform. The kappas are, again, just parametrizations on the spherical harmonic basis. And then you stack a few of these layers, and the way then you predict is just in an autoregressive way. So you train something to predict from one step to the next, and then you compose it.
Okay, so then what I'm really trying to understand is how generalizable is this? To what extent can I just shove a random simulation to work with one of these methods, and to what extent they're cross-operable?
Well, I think you have to be smart about how you design the method, and the method has to be designed for the simulation that you're thinking about. So this, I mean, if you try to use, the fluid simulation that I had before with this kind of method, it wouldn't work. One, this is designed particularly for the sphere, right? Because it uses spherical harmonics. and also it's tailored to the problem, right? Things are trained in such a way that you try to predict things auto-regressively from one state of the atmosphere to the next. Here, you're doing something completely different, because here you're trying to capture the information of the car and then trying to map that onto the actual output, which is, the pressure. And
there's no time here.
There's no time here. No, there's no time here, because these are RAND simulations.
Okay, so yeah, really what I'm figuring out is I have a simulation. I'm an expert. I understand my domain is incomplete, but I want to approximate that. To what extent are we close to having a like here's 50 solving methods. One of these are going to work for you.
I think we're. It's a good question. I think we're relatively close to. It depends on data and it depends on the problem. I don't want to make big claims of we're close to solving all. I don't think we are. There's still tons of problems which are very hard, and you can see that through the approximation theory. I think there are kind of enough methods out there now that something will fit the problem which you're trying to get at. But I think, you're going to have to, I think there's nothing generic out there yet. So if you want a really good solution, you're going to have to try and tailor whatever kind of generic method you start with to the problem that you're actually solving.
I see. Okay. So then if I have, let's stick to spheres, because system things are actually not the fun bit. If it's regional, it's not a sphere. Let's say if it's a sphere, to what extent do I start with spherical harmonics?
Yep.
And to what extent do I say, well, this part of the sphere is actually notably different. I have to, wavelet it for that resolution. In fact, a regional model would be a wavelet because mountains matter and they're different from everything else.
Absolutely. So if you want to do something local, then it doesn't really make sense to do the spherical harmonic thing, right? Then wavelets might be a better way to go, or a different architecture could be a better way to go. I don't have a generic answer of this is the best thing to do, because I don't think it's out there. I think that's a big open problem in this field, right? People are kind of doing almost random things in the sense that, a whole host of things are being tried and shown to work on this problem or that problem. But as far as I know, there's no unifying theme of this works really well for this, other than the fact that convolutional neural networks have worked well for images. I think that's kind of the only unifying theme so far.
Let me just a very pragmatic question. Is there even a way of doing bake-offs where everybody using the same interface, so you can try algorithm A with solve problem B? Or is it like research project, like burn a grad student at every experiment?
Yeah. I mean, there's a few libraries out there. We have a library for some of these methods that we're kind of trying to keep consistent. But honestly, no.
Okay, no, that makes sense. Cool. Yeah. Well, thank you very much. I don't know if you want to go through your conclusions, but this is fascinating.
That's okay. I mean, there's a lot. The point of this conclusion is that this is a really brand new field in some sense.
Yeah.
And there's tons to do, both in terms of the approximation theory. I think we kind of know nothing about how to actually properly characterize approximation spaces. And also, we know nothing about how to connect the optimization to the approximation results. All approximation results I showed you there exists. And like you had a really good question about, how did I actually prove this? And I said, well, I just emulated a numerical method. But clearly, that's not what's happening in the optimization, right? The optimization is doing something else and giving a truly different solution. So we kind of still have no way of understanding that. So there's tons to do, and there's tons of practical things to do in terms of, like you mentioned, unifying all of this together and kind of trying to figure out, what is best for what, and giving really practitioners a good way to interact with all of these methods.
Right. And then one more question. What is the state of average case analysis or probabilistic analysis, where it's like there's this probability of finding a solution in the space, which those tend to be closer to average case analysis?
You mean for the approximation?
Yeah, because the average case would be fantastic. Like, given that the data looks like this, I can on average, proving an average convergence is hard.
Yeah.
But maybe there is such a thing says that the probability of approximating this with so many parameters is this, and it trends towards one with so many samples or something. There's at least a long way to average case analysis.
So I would say that anything in high probability will be just as bad as the average case analysis. But this is not something this is not a field that I'm super familiar with. Yeah.
Okay, no, and that's really hard. But yeah, thank you very much. This is fascinating.
Yeah, thank you so much for having me. This has been fun.
Yeah, have a good day. Bye.
Okay.